This is Columns Part 1 of the Structural Design section of our Aeronautical Engineering course. We generally think of columns as long vertical posts that hold the tops of buildings up in the air, like the Parthenon, for instance. See all those columns holding the top of it up? That's what we generally think about when we hear the word columns. But each segment on this truss here, each segment that's in compression, can be considered a column. This is a 10-foot long tail boom mock-up. See, there's one end of it where the tail of the airplane goes on. Here's the other end. It's a 3-flanged truss. It has a top flange that's in tension and 2 bottom ones that are in compression. What we're going to look at is this particular one right here. This is the one that gave way when this tail boom was tested to destruction. Notice it bent in the middle. That's where they bend. This piece here is 13 inches long. We'll draw it out and analyze it. If you want to see this tail boom from a distance, just go on YouTube and search for 20 seconds over Reidsville, and you can see the maiden flight of the airplane that has a tail boom like this. But this one was a mock-up that one of my nieces and I destroyed as a science project. We did it after I flew the airplane. You're supposed to do that sort of thing before you fly airplanes, but better late than never, I guess. Okay, a nail. Let's say here's a nail head. There's a nail. Okay, and there's the point of it. And here's a board. Okay. Well, that nail has a much longer column than a nail that's already been hammered into the board. And the longer nail, the nail that's just getting started going in the board, is much more likely to bend. Long columns are weak and short columns are strong. The strength of a column isn't necessarily related to the strength of the column material. The column strength is more related to the stiffness of the column material. An example of this concept can be seen by comparing carbon steel, which is cheap steel, to stainless steel. That's the pricey steel. The carbon steel has a greater modulus of elasticity. It's not much greater, but it is slightly greater, which means it's a little stiffer than that of stainless steel. But stainless steel can withstand more stress. It can take more pounds per square inch. The modulus of elasticity, we use the letter E to denote Young's modulus. The modulus of elasticity, it's an indication of the stiffness of the material. It's defined as stress divided by strain. Okay, so what are stress and strain? Okay, if a material is stressed to 30,000 pounds per square inch, let's say that equals 30,000 pounds per square inch. Okay, and let's say it becomes shorter if it's being compressed or longer if it's being pulled. Let's say its length changes 1/1000th of what it was to begin with. Well, then the strain in this particular case would be 1/1000th, which is 0.001. So 30,000 pounds per square inch divided by 1/1000th is like same as multiplying 30,000 times 1,000. So Young's modulus for this particular case would be 30 million pounds per square inch. The higher the modulus of elasticity is, the stiffer the column will be, and consequently the greater will be the load that the column will bear. The strength of a column is also determined by the way that the ends of the column are supported. The strongest columns are fixed at both ends. See, here are 4 columns. This one is fixed at both ends. It's welded or surrounded by concrete or whatever. In other words, it's made to where this is held rigidly in place. And that's the strongest column, fixed at both ends. Next strongest is fixed at one end and pinned at the other. By pinned, I mean it has a hole in it and something round like a nail or a bolt or a rivet goes through that hole. Okay, then next strongest are the ones that are pinned at both ends, and the weakest columns of all are the ones that are free to swing any way they want at one end. Okay, here's the equation that is used to estimate the strength of a column. A math teacher I had in college pronounced it Euler, and if you look it up, they'll tell you that's the proper pronunciation. Of course, that sounds kind of strange to me, the letters EU pronounced Oi. I mean, whoever heard of an euphemism or a guy named Eugene? But if you want to pronounce it that way, you can. I'm just going to call it Euler. Anyway, this is Euler's equation. The force, the critical force that a column will bear is equal to N times pi squared times E, which was our modulus of elasticity, Young's modulus. Okay, and this I is moment of inertia. That would be the area moment of inertia of the cross-section of the beam that we're considering. And L is the length of the beam. So this N, it varies from 0.25 to 4. So N is 4 for the strongest of columns, those that are fixed at both ends. N is 2 for fixed at one end, pinned at the other. N is 1 for a column that's pinned at both ends. And N is 1/4 or 0.25 for a column that's free at one end. This equation can be found at the website engineeringtoolbox.com/Euler, EULER -column -formula D as in Delta _1813.html. So F there is the critical load or force at which the column will buckle. N is that factor that is determined by the way that the ends of the column are supported. As I said a minute ago, I'm just running over my paper, making sure I cover all the bases here. 4 for fixed, 2 for fixed pin, 1 for pin, 0.25 for fixed free. E is modulus of elasticity, I is moment of inertia, L is column length. Okay, here's the way some other people like to see Euler's equation. Instead of saying F equals N times pi squared times EI over L squared, they say F is pi squared times EI over KL squared. Well, that's really the same equation as this one. The only difference is that one of them uses the letter N in the numerator, the other uses the letter K in the denominator and puts it inside these parentheses and lets it get squared. So, as you might have guessed, when N is 4 for a fixed, well then K would be 0.5, because 0.5 squared would be 0.25, and 1 over 0.25 is 4. So when N is 2 for fixed pinned, and when N is 2 for fixed pin, well then K is 0.7. Actually it's 0.707. It's square root of 2 over 2, because 0.707 squared is 0.5, and 1 over 0.5 is 2. So if N is 2, K is 0.7. When N is 1, well that makes it easy. K is 1. And for the columns, the weakest of all, N would be 0.25 and K would be 2, because 2 squared would be 4 and 1 over 4 would be 0.25. This formula can be found at the Wikipedia website. It is en.wiki/structural_engineering_theory, and that would be in the buckling section on that website. And you'll also find this equation in the same buckling section. This equation saying about the same thing this is saying. This is force, but this is stress. The Greek letter sigma is used to talk about the stress in the material of a column. The formula looks sort of like that one. It still has pi squared and the modulus of elasticity, but it doesn't have moment of inertia. In this case, it has the K and the L underneath, but it has this lowercase r, which stands for radius of gyration. If you watched our gyroscopic precession video, you're familiar with the term radius of gyration. It was defined as this would be the mass radius of gyration. It was defined as the radial distance from a given axis at which the mass of a body could be concentrated without altering the rotational inertia of the body about that axis. Well, when you're talking about a beam cross-section, you're talking about area radius of gyration, and you could describe it with almost the same words. You could call it the radial distance from a given axis, a centroid axis, at which the area of a body could be concentrated without changing the moment of inertia of that body, because moment of inertia is area times the square of its distance to the centroid axis. Okay, you may remember in our gyroscopic precession lesson how we determined that the radius of gyration of a disk was about 0.707 times the radius of the disk. A disk like a millstone or a big old cheesecake or something like that. But the radius of gyration of a ring was equal to the radius of the ring, because all the mass of the ring is out there where the ring is. There's nothing but air inside it. Whereas a big old cheesecake dish has cheesecake all the way from the outer edge to the center of the cheesecake. Here's a propeller and here's a baseball bat. You may think it's strange that we're talking about propellers and baseball bats in our columns lesson, but I want to explain this radius of gyration concept. You have two different kinds of radius of gyration: a mass radius of gyration and an area radius of gyration. The mass radius of gyration is at about 55% of the way from the center of a propeller to the tip, but it would be closer to the right end of a baseball bat because the propeller is massive in the center and thin at the tip, whereas a baseball bat's just the opposite. It's more massive toward the right end. Now, the radius of gyration of a cross-section of a beam would be the area radius of gyration. The radius of gyration of a propeller or a bat would be a mass radius of gyration. But as I said earlier, it was defined as, how did I say that? Well, we'll get back with that. We're about out of time. See you in part 2.